recording, or I forget. Started forgetting things now that things are getting a little nicer out here. Okay, the recording is in progress, unmuted. All right, can people hear me?
Yes, we can hear you.
All right, thank you. Okay, so I hope all of you had a nice weekend. Just remind you of the one last remaining event of the semester, the summer session. That's just the test based on 5.5 and chapter 6 and 7. Okay, whatever we are covering after test number 5. There is no cumulative final exam. I hope all of you know that. Okay, so next week you shouldn't be waiting for me to give you a 2-hour final exam based on the entire course. Any questions about any of that? I hope I'm not surprising you by writing that down. Okay, so last lecture we just started doing examples with eigenvalues, but we didn't really talk about any of the theoretical aspects of what exactly you expect. Mainly because I was in a limited Blackboard space here and it is a short lecture. Okay, so today everyone is kind of fresh, so I'm going to write down what you need to kind of expect when you do these eigenvalue problems. Okay, so last lecture I think we did 2 examples with eigenvalues. And it's very easy to get our heads kind of buried into these calculations and forget about everything else, but it's nice to understand what exactly is going on behind the scenes. Okay, so if A is a n by n matrix, remember that lambda is a eigenvalue. If A times x equal to lambda times x for some non-zero vector x, okay. And that part is important because if x equal to 0, the equation is obviously true, and it's of no particular advantage to us. And this non-zero vector is what you call as the eigenvector for the corresponding eigenvalue lambda. So usually it comes in a pair. So if you see this word eigenpair, that usually means there is an eigenvalue and corresponding eigenvector. Okay. So some textbooks kind of throws these words around randomly. So the eigenpair means that there's an eigenvalue and the corresponding eigenvector. Another word for this is the basis for the eigenspace. Okay, that's because you're finding the null space of the matrix A minus lambda I, and then you're writing the vectors that span the null space. Okay. So it's a very fancy way of saying it, but at the end of the day, you're just solving this homogeneous system with x equal to 0 not being a possible answer. Okay. So we're looking for the non-zero solutions of this equation, x not equal to 0. And that is why we start with the determinant of A minus lambda I equal to 0. Okay. And then once you get your lambda, you go back and find your corresponding eigenvector based on that particular eigenvalue. Okay. So it's called the basis for the eigenspace because when you're doing the eigenvector, you're actually finding the null space of the matrix A minus lambda I. In other words, you're trying to find the basic and free variables and writing the basic variables in terms of free variables. Okay. And that is actually what you call as the basis for the null space. And in this case, that null space is the eigenspace because you're doing. So people might throw these random terms around and they kind of mean the same thing. Okay. Now to show some of the facts that I'm going to illustrate here, okay, let me just mention like a couple of simple things about high school algebra. Okay. You have a quadratic equation like this, x square minus bx plus c equal to 0. I purposefully set a equal to 1. So it's just x square minus bx plus c equal to 0. Okay. The roots of this are given by, of course, so you know this, negative b, which is b plus or minus the square root of b square minus 4ac divided by 2. So you have two roots here. Okay, so you can call this as r1 equal to b plus the square root of b square minus 4c over 2, and r2 equal to b minus the square root of b square minus 4c over 2. And this is one of those things that your high school teacher may have mentioned in passing, or maybe you did a few problems. Okay, if you add these two roots, r1 plus r2, there's plus or minus the square root of b square minus 4c terms. They get cancelled out. Okay, and you get b over 2 plus b over 2, which is b, which is the negative of this coefficient here. Okay, so I think in your high school you may have seen it as negative b over 2a. That's the same thing. Similarly, if you take the product of those two roots, a little bit of a annoying calculation that you have to do. You have to do a square minus b square thing. Okay, and eventually you'll get this. You have b square, and then you have minus b square minus 4c divided by 2 times 2, which is 4. Okay, and that's equal to c. Okay, so the sum of the roots is the negative of the middle coefficient, and the product of the roots is the last term or the last coefficient. Okay. We will make use of this in a nice way in the context of eigenvalues. Okay, so just hold on to that thought. I didn't want to do that while I was writing things down. So if I write this down early, I can refer to this later. Okay. All right, now let me write down a few facts about eigenvalues, which you might find useful. I don't know if you got a chance to do this homework or whether you're waiting for me to show a few more examples and then do it. Okay. Irrespective of that, I told you that the starting step is always going to be the determinant of a minus lambda I equal to 0. Okay. It doesn't matter whether you write it as determinant of a minus lambda I equal to 0 or the determinant of lambda I minus a equal to 0. Both are correct. I mean, it should be obvious, okay, but sometimes when some students, when they see this, they think that they're probably looking at the wrong answer or something. Okay. Both these are correct. Just stick to one of them, whichever is easy for you. Don't try to switch between the two during the problem. Okay, that might be confusing, but both are correct. Yes, a minus b equal to 0, b minus a equal to 0. Okay. Statement 2. For a n by n matrix, you're always going to get a nth degree polynomial. So the determinant of a minus lambda equal to 0 always gives you nth degree polynomial equal to 0. Because when you do it by hand, you don't want to do anything more than degree 2 or 3, but it could be any degree in theory. Right? And one of the guarantees of algebra is that if you set an nth degree polynomial equal to 0, always be n roots. Okay. Some of them might be imaginary, some of them could be repeated, some of them could be dirty looking, but at the end of the day, there are always n roots for a nth degree polynomial. This polynomial is what we call as the characteristic polynomial for the matrix. Okay. Almost like the characteristic equation for your differential equation. So take something and you convert it into corresponding algebraic equation. It's always the characteristic polynomial or characteristic equation. Okay. So every matrix has every square matrix has a characteristic polynomial of that same degree as the size of the matrix. And you're always guaranteed n roots. Once again, that doesn't mean that you can always solve for it easily. Okay, that's not what I'm saying. But algebra guarantees there are always n roots for a nth degree polynomial equal to 0. Now, when you do problems in this course, what can you expect? It's usually a 2 by 2 or a 3 by 3. So it's nice to sort of have some idea about what kind of situations you could end up in. All right. The 2 by 2 case is pretty easy because we have talked about this even in differential equations. Okay. So 2 by 2, it's a quadratic equation or a quadratic polynomial equal to 0. And all of you have seen enough math at this point to know that it has 3 possible roots. Okay, either R1 not equal to R2, both are real, or R1 equal to R2, both are real, or R1 not equal to R2, both are imaginary. You cannot have one real and one imaginary root. I mean, I hope all of you agree with me on that. You cannot have one of these and one of that. It always comes in pairs of plus or minus of the square root of that term. So when these roots are repeated, it kind of creates a problem. Okay. With eigenvalues, especially when you try to apply it to other situations, those repeated eigenvalues are always a little bit of a thorny issue. So we need to give some conceptual names for these things. So let me just write it here. So number 3, the algebraic multiplicity. I'm going to just denote it by M subscript A for future reference. Algebraic multiplicity is the number of times a root is being repeated in that particular polynomial. It's the number of times an eigenvalue is repeated. It's not necessary that there is a repeated eigenvalue all the time. Okay. If it is repeated, that is when we have to think about algebraic multiplicity, which is not equal to 1. So the default value is 1 when the eigenvalue is not repeated. That is what happens here and here. Okay. So in this case, this has algebraic multiplicity of 1. This has an algebraic multiplicity of 1. Same thing here. This has an algebraic multiplicity of 1. Same here. So it's usually not a problem unless there is a repeated root. Okay. That is when you look at this. Okay, there are the eigenvalue here is repeated twice. So the algebraic multiplicity is 2. It's a count, really, right? If it is not repeated, no problem, it's just 1. It is repeated, just count it and write the number of times it's repeated. So you'll see this is one of those side questions. Find the eigenvalues and state the algebraic multiplicity, which means just count the number of times it's repeated. Okay. So since we wrote algebraic multiplicity, let's also write what geometric multiplicity means. Multiplicity. Again, let's abbreviate it by mg. And this is the number of eigenvectors or it's a number of free variables. Okay. It's a number of eigenvectors for each eigenvalue. when both these concepts here, the algebraic and geometric multiplicities, it's an issue when there are repeated eigenvalues. Okay. So the default value is 1. So mg equal to 1 when ma equal to 1. Always. Okay. Which means that if there is a non-repeated eigenvalue, you get it 1 and exactly one eigenvector out of that one. If ma is more than 1, then we don't know. So like for example, in this case, okay, we cannot really predict how many eigenvectors you will get unless you see the matrix. So if ma is greater than 1, mg is greater than 1, but it's going to be strictly less than ma. Less than or equal to ma. Okay. Cannot grow bigger than the size of the matrix. So the count is always limited to however or how many ever number of times that eigenvalue is repeated. So another way of looking at this is the number of free variables that you get in the A minus lambda I matrix. Okay. Those are the same thing because it's a number of free variables that generates the eigenvectors. If you get one free variable, the geometric multiplicity is 1. Okay. Once again, there should be no surprise here. If there is no repeated eigenvalue, the geometric multiplicity is always 1. So write those two things carefully. Okay. Those are kind of frequently occurring in all the problems that you'll be doing. Okay. It's a very simple detail. You just need to look at what you have done and count the number of things, but don't confuse the two things. All right. Any questions on those two? I'll do some examples, so don't worry about those two things. Okay, but any questions about the definitions of those two, the multiplicities? Okay, now let's make use of what we just did up here. Okay, this is probably one of the more interesting properties of eigenvalues and eigenvectors. Let's take a 2 by 2 matrix like this, say A11, A12, A21, A22. So it's the way to start your eigenvalue would be to write the determinant A11 minus lambda, A12, A21, A22 minus lambda equal to 0. Okay, that is where you always start. Okay. And let's expand this. For a 2 by 2, it's not a big deal. For a 3 by 3, it looks ugly if you don't have numbers, but so it's not too bad. Okay. So it's going to be A11 minus lambda times A22 minus lambda, okay, minus the product of those two equal to 0. So if you expand this, you get lambda square. Okay, that is the actually that's the last of those 4 terms when you do the FOIL. Okay. Lambda square minus you have A11 plus A22 times lambda. Okay, that is going to be this term and this term. Plus there's the product of those two, A11, A22 minus A21, A12. The reason I wrote this down in this form is so that you could look at that matrix and see what those terms are. Okay. If you look at this middle coefficient here, that is the sum of these two terms, which is what you call as a trace of the matrix. So if you go into the MATLAB world, okay, this is what you call as a trace of A. So trace is the sum of the numbers along the main diagonal. For a 3 by 3, it's going to be 3 numbers because A11 plus A22 plus A33. Now, if you look back at what I wrote up there, okay, the sum of the roots, which is going to be the sum of the eigenvalues, is always equal to the trace of the matrix. Okay? That is a universal truth. So lambda 1 plus lambda 2 is equal to the trace of A. That's a nice way to check your answer without doing any complicated calculations. Take your eigenvalues, you add them, okay, and if you add the numbers on the main diagonal of your matrix, they should be the same number. Not only that, the more important one is the product of those two, lambda 1, lambda 2. What does this quantity here represent? A11, A22 minus, if you look at that 2 by 2 matrix, what is that thing?
The determinant?
It's the determinant, okay? So the product of the eigenvalues is always equal to the determinant of A. No, so the determinant keeps on appearing here and there. Okay, now you can probably build a relationship between the invertible matrix theorem and the eigenvalues and so on. Okay, anytime the determinant comes in, it just throws a bunch of statements at you. So let's write this as a nice result, okay, which is always handy to check your calculations if you want to. Okay, it's also useful for other statements which you might think would be useful. So result number 4. For any n by n matrix A, so this is true for any matrix, okay, not just for 2 by 2. The sum of the eigenvalues is always equal to the trace of A. And the trace means the sum of the numbers along the main diagonal. Or the entries or numbers. And the product of the eigenvalues I want you to pay attention to the second one. The first one is mainly like a visual check. Okay, this one is the more important one because it kind of now creeps into your invertible matrix theorem through a back door. Okay, so the product of the eigenvalues is equal to the determinant of A. A lot of students write it down and then they pretend that they didn't see it. How do we have 2 lambdas for what? Can you tell me which one we're talking about here? Or?
Yeah, after showing the proof, we had lambda 1 plus lambda.
Because it's a quadratic.
Oh, yeah, sorry, yeah.
It's a second degree polynomial, so there are 2 roots. Right, so maybe I should have written it. So these are the 2 roots of. Okay, now let's play some games with that statement. Okay. I can erase this because I used this result there. Statement number 5 is okay for matrix to have 0 as its eigenvalue. Okay. There is absolutely nothing that will stop you from doing it. But what is the thing that is not okay? This is okay, but what is the thing that is not okay? To have 0 as the eigenvector. Okay, that is not okay. That's when I get offended. Okay, so it's not cool to have 0 as an eigenvector. I see that I get very angry, so don't do that. Okay, so 0, it's possible for a matrix to have 0 as eigenvalue. Take the 0 matrix. Okay, so there is nothing else that could happen there. One zero is an eigenvalue because of this statement here. Okay. The determinant is forced to be equal to 0. So if 0 is an eigenvalue, then the determinant is equal to 0 for the matrix A. No matter what else is going on there. Okay. You probably have no idea what the matrix would look like, but you know the 0 is an eigenvalue, so the determinant is equal to 0 because of that property there. Which also means that A is not invertible. And all the other statements that follows from it. Okay. I'm not going to write everything because I've done it so many times. About the rank and linear independence and basis and all kinds of things. Okay, so that's number 5. The 6th one, I don't think you should probably worry about this, but just to kind of cover all base here. Okay, please do not raw reduce the matrix A before finding its eigenvalues. I know the semester, one of your instincts is to take the matrix and start doing your R3 minus 2 R1. Okay, don't change the matrix because it changes eigenvalues. In other words, the eigenvalue of A is not the same as the REF of A. Sometimes I've seen students try this stunt, and it's a terrible thing to do. Okay, so don't do that. Okay, I think I've mentioned everything necessary to do the problems and understand what we are trying to do this semester. Okay? So don't forget about the multiplicities and also the determinant property here. The product of the eigenvalues is always equal to this. So just to illustrate that these things are indeed true, okay, let's just look at the 2 examples we did on Thursday before we do any new ones. So last Thursday's examples. We did 2 of them, one 2 by 2 and one 3 by 3. The 3 by 3 was pretty straightforward actually. I think the first one was this 1, 4, 2, 3. And we calculated the eigenvalues as 5 and -1. Let me know if I'm missing something. Okay. And we got an eigenvector out of each. So is that okay? 5 and -1. Okay. So let's check whether our claims are true. Okay. So lambda 1 plus lambda 2 is 5 minus 1, which is 4. The trace here is 1 plus 3. 4. Yay. You might think, okay, there are different numbers that could add up to 4. What if I got, say, 2 and 2 here? You know, how do you know? And that's when you could probably check the determinant as well. For a 2 by 2, it's not too bad. Okay. So the determinant of this is 3 minus 8, which is -5. The product of these 2 numbers is also -5. So for a 2 by 2, it's a pretty simple check. For a 3 by 3, finding the 3 by 3 determinant may not be always a time efficient thing to do. Okay, but it's worth a thing to do if you are not sure of your answer. And in this case, the eigenvalues were not repeated, so the algebraic multiplicity was 1 and 1. So if there is no eigenvalue that is repeated, the multiplicity is pretty much formality. The second example was a 3 by 3, and you need to remind me what those numbers were. 1, 0, 1, 2, and 0, 0, 2. Thank you. And for this case, I got the eigenvalues to be lambda 1 equal to lambda 2 equal to 1 and lambda 3 equal to 2. Okay. So this is where the multiplicity thing starts to kick in. Okay. So for this eigenvalue, the algebraic multiplicity is 2. Okay. Nothing wrong here. This is just 1. When you add them together, you should get the total number of eigenvalues always. Okay. Let's also check the geometric multiplicity for this. When you did this eigenvalue for this particular matrix, okay, you got just one eigenvector, V1, thing which was 1, 0, 0. Okay. There was no other vector there. Okay, that is not your fault. Okay. There was only one free variable, which was x1. So there is only one eigenvector, and that is when your mg is equal to 1. So there is no way to say what is going to happen with the cases where the multiplicity is more than 1. It could be same as this or less than this. Okay, that depends on the matrix. Second case, it was nothing surprising. Okay, this is always true because we got exactly one eigenvector. I think it was 7, 3, 4 or something. I forgot. Okay. So just keep note of this thing here. Okay, MA equal to 2, MG equal to 1 for this matrix. Not always true. Okay, for this matrix. And let's also check the trace and determinant. Maybe the trace would be 1 plus 1 plus 2, which is 4. Okay. And the sum of the eigenvalues, lambda 1 plus lambda 2 plus lambda 3 equal to 2 plus 1 plus 1, 4. Okay, exciting. And the determinant, it's a triangular matrix, is 2 times 1 times 1, which is 1. 1 times 1 times 2 is 2. So lambda 1, lambda 2, lambda 3. All right, so now we have all the kind of theoretical details you need for this course, okay, or this eigenvalue concept. Now let's try to do a few more examples today, and then at some point we will make the transition back to differential equations. Okay. Any questions about any of these? I've been speaking for a while now. Any questions? All right, so let's do one example with imaginary eigenvalues, because that's one of the topics that the College of Engineering wants us to do. Okay, because it's very important for your applications later. So find example 1 for today. Find the eigenvalues. And I'd also mention a very important theorem while you're doing the example, okay, because of the nature of the theorem. Makes sense if you write it during the exam. Find the eigenvalues and an eigenvector for the matrix A equal to 2, 3, 3, 2. And just for practice, you can also state the algebraic and geometric multiplicities, though there's nothing exciting here. Okay. All right, can you write the characteristic polynomial and see how that comes out, and I'll slowly follow. Okay. Oh, I need a negative here, sorry. That would have been kind of an easy problem. Just change the A12 to a -3 so that it becomes more attractive. Once again, I changed that A12 to -3, so that it becomes more relevant. Okay. All right, so this becomes 2 minus lambda whole square minus -9, that is plus 9, equal to 0. You could expand this out and then solve it as a quadratic, or you could do the following. Okay, it's up to you. 2 minus lambda whole square equal to -9. As long as you don't expand this, you can always push this to the other side and take the square root of both sides. So 2 minus lambda equal to plus or minus the square root of -9. If you're doing this, just make sure that you put plus or minus on the right side. It's not just square root of -9. Okay. That is what you call as 3i. So 2 minus lambda equal to plus or minus 3i. So there are two eigenvalues here, both of which are imaginary. I don't care which one you call as lambda 1, lambda 2. The quadratic always has two roots. This is 2 plus 3i and 2 minus 3i. If you want, you can do a visual check. If you add those two, you get 4, and the trace of the matrix is 4. I don't expect you to know a whole lot of complex number theory to do this course. Okay. One thing you should know is this, that definition of I is the square root of -1. So that also means that the square, I square is -1. You might need this when you simplify some of the eigenvectors. So please, make sure that you clearly observe these two cases. And if there is an I square, that's a real number, -1. Okay. So we need to find an eigenvector for each of these eigenvalues. Okay. So if it was a real eigenvalue, you have to do it for each one of them. Okay. Complex numbers gives you a nice shortcut. If you observe here, the only difference between these two is the positive and negative sign here. Okay. The 2 and 2 are the same. The 3i and 3i are the same. If there's anything different, it's just the plus and the minus sign. Okay. So this is what you call as the complex conjugate of lambda 1. So anytime there's a conjugate of an imaginary number, that is when the sign of the I term changes. So the complex conjugate of A plus bi is A minus bi and vice versa. Not change the sign of the A term, that is not our business. Okay. It's the B term that is switching the signs and creating its corresponding conjugate term. You've probably seen the word conjugate even for square root terms, but here it has a particularly important role to play. Okay, here comes the first of the important theorems that you will find useful to save some time in your calculations. Theorem, it's useful and important. You're going to take advantage of this conjugate property of the eigenvalues. Okay. Since the only thing that is changing there is a sign, it's reasonable to expect that's what you should expect in eigenvectors as well. So if lambda 1 equal to A plus bi is an eigenvalue with an eigenvector. There is nothing called the eigenvector because it's based on a free variable. You can generate infinite number of possibilities. Okay, so with an eigenvector, v1 equal to, I don't know, u plus iv. I hope I won't regret this notation. So with an eigenvector, v1 equal to u plus iv, here is the good thing. Okay, then an eigenvector for the second eigenvalue, which is lambda 2 equal to a minus bi, will be v2 equal to u minus iv. So theorem is saying that if you have a conjugate situation, okay, you don't have to redo the calculations for the second eigenvalue. You can just change the sign of this to a negative because it came from the same a and b up there. Okay. So as much as complex numbers are annoying, it comes with a good thing that you only need to do one eigenvector because the second one is always a conjugate. So now let's focus on one of the eigenvalues. I don't care which one you do. The other one is always a conjugate. Okay. I always try to do the positive one, but it's your choice. Okay. So for lambda 1 equal to 2 plus 3i, since I decided to call that as my lambda 1, I just stick to that. Okay. So you need to find the null space of a minus lambda 1i. That is going to be 2, negative 3, 3, 2, minus lambda 1i would be 2 plus 3i, 0, 0, 2 plus 3i. Write this down step by step because, if you're not used to calculating things using imaginary numbers, you don't want to do too many things at a time. Be careful here. There is a subtraction going on here. There are two terms. It's always a nice habit to put parentheses here, okay, just so that you distribute this carefully. And then you get 2 minus 2 plus 3i. That's going to be negative 3i, negative 3, 3, and negative 3i. Once again, there are lots of telltale signs that your eigenvalue is correct. If you look at that matrix, it looks kind of sitting ready to get a 0 or a row full of zeros. Okay, so let's first try to get this into an REF carefully. So let's do negative 1/3 R1 and 1/3 R2. Unless you are really comfortable with operating on I, okay, this I, just do ordinary things. Don't try too many fancy things here. So it's going to be I 1, 1, negative I. And now you can switch R1 and R2, okay, so that you could bring the 1 to your favorite position there. That's going to be 1, negative I, I1. So if you're an electrical engineer, you probably might prefer writing J there because I is always electrical current for you, but you'll just stick to I. Okay. All right. Do your typical REF, except that this is I, so you have to do R2 minus IR1. If it was 5, you would have done R2 minus 5R1. So R2 minus IR1. You know what to expect, right? You need to get 0 here and here, 0 here. No exceptions to that rule. So this is 1, negative I minus I is 0. Now you want to write a 0 in the next one, but you're not sure. Is it really 0? So it's going to be 1 minus I times negative I. You don't have to write that, but just to convince you that this is 0. Okay, and this is 1 plus I square. Are we in trouble? No, I square is negative 1. Okay, it is 0. So there you have it. So if your eigenvalue is correct, you must have a row full of zeros. Okay. So it's 1, negative I, 0, 0. Good news. Always a relief when you see this because you know then there is one free variable here. Okay. And in terms of geometry, the eigenvalues which are imaginary not really scales it, it also rotates it by a certain angle, okay, which is a little bit beyond the scope of this course. That's why I'm not going into all those details, but it's just not a straight line at this point. It also turns around with an angle. Okay, so let's go to that REF. So x2 is free. Let's set that equal to some letter u. And the first row gives you x1 minus I times u equal to 0. Okay. So I is part of the calculation. You cannot throw it away. So x1 is I times u or u times I. Okay. So the general eigenvector x1, x2 would be u times I1. Okay. As always, pick a non-zero value for u. Okay, the safest choice is u equal to 1. Some students have said, oh, why don't we pick u equal to I? That way we can make it real. It won't happen because then this one is going to kill it. So there's no need to try anything fancy here. For u equal to 1, get an eigenvector v1 equal to I1. So you do all the hard work for that one eigenvalue because now we can use our beautiful theorem up there and write the second one without any work. Okay. So then by our lovely theorem, okay, that one, for lambda 2 equal to 2 minus 3i, and eigenvector v2 would be negative I. Okay, remember, it's just conjugating it. The sign of I should change to a negative I. 1 will remain as 1 because that's a real number. Because if you multiply both by a negative, it's just a multiple of that vector. Okay, so don't do that. So it's negative I1. Now, if you are really not convinced about that is true, you could always sit down and do the calculations. You will get the same answer. Okay, but you don't have to. Please don't try this stunt on real values. Okay, it's only for imaginary eigenvalues where the conjugating applies. So just limit the scope of this to only those examples where you see an I. Yeah, so it's just 2 by 2 imaginary is the only thing that I expect you to do with I. Okay, so the only difference would be different numbers, but the concept is the same. And we'll come back to this tomorrow when we do differential equations. So just don't forget it. Okay, just keep it. Any questions about that example? If you understood this, you should be able to do any 2 by 2 matrix at this point. Any questions? All right, so far we have been kind of drinking Kool-Aid here. Okay. Let's do some really hard-looking 3 by 3 determinants just to get a feel of how things could go bad. Example, find the eigenvalues and the eigenvector for each eigenvalue. Okay. Oh, I forgot to write. I think it's pretty straightforward. Both MA and MG is equal to 1 for both. Okay. There is no repeated eigenvalue, so there is nothing going on there. That's a pretty boring case. All right. Try this yourself. 877 5309, -7, -6, -7, 778. Take your time. Okay, it's not, you'll get some clean eigenvalues, but you have to work for it. And please don't do any REF. And also state the algebraic and geometric multiplicities. These are pretty nice examples to illustrate these things. We'll expand this around the first row. Okay. There's nothing attractive about anything else here. So Okay, so I'm not really trying to take any shortcuts. Okay, just do it in an organized way so that we know what's going on here. So this would be negative 56 plus 7 lambda plus 49, and this would be negative 49 plus 42. Okay, that is going to be negative 7, and then we have plus 7 lambda, and this is 7 lambda minus 7. So if you kind of look carefully at those two terms, and we're going to actually be very happy about what's going to happen here. This is negative 7 times 7 lambda minus 7. That's a plus 7 times 7 lambda minus 7. Okay. Couldn't be more happier. What is the net sum of these two terms? 0, right? So we only have to worry about this term now. Yeah. So 2 of the headaches are gone, 1 remaining. And let's expand this. It's going to be negative 48. That's going to be plus 6 lambda minus 8 lambda. That's going to be minus 2 lambda plus lambda square plus 49. And that becomes lambda square minus 2 lambda plus 1. Since the other two terms are not there, we only need to look at the first term, which is 8 minus lambda. Don't forget this. Okay. 8 minus lambda times lambda square minus 2 lambda plus 1. Equal to 0. Okay. Here is my question to you. What do you do next? Do you expand it out? You could do that. It's a free country, but is that going to make your life worse or easier? What is the best thing to do now? What is this part equal to? It's lambda minus 1 times lambda minus 1, or lambda minus 1 whole square. Okay. So there are 3 eigenvalues. This is a repeated eigenvalue. That one is not. Okay. So you can number it whichever way you want. We could do this as lambda 1 equal to 8, and lambda 2 equal to 1, and lambda 3 equal to 1. Make sure that you list everything, even if they're repeated. Okay. Don't throw away the ones which are repeated. Okay. Keep everything so that you know there are 3 eigenvalues for a 3 by 3 matrix always. So this one has a algebraic multiplicity of 1, and this one has an algebraic multiplicity of 2. Whenever this happens, there is something exciting to look forward to. We never know what's going to happen there. Okay. This one we know it's going to give you one vector. Mg is 1. Okay. When Ma is 2 or 3, it's just left to the matrix to figure out what's going to happen. All right, so it is not too bad, but if you do it carefully, it's very easy to make mistakes here. Okay. Because there are lots of positive and negative signs. Now let's find an eigenvector for each of those. So A minus 8i would be 877, negative 6, negative 7, negative 6, negative 7, and 778 minus 800, 080, 008. You should get only one free variable and exactly one free variable out of this. Okay, no exceptions in this case because it's not a repeated eigenvalue. So we kind of know what to expect here. So 0, 7, 7, -7, -7. I was about to say 2. No, it's -7, -14, -7, okay, -6 minus 8, and you have 7, 7, 0. It's 2 times. I was about to say the wrong thing and I corrected myself doing that. So now that is not too bad because everything is a multiple of 7. Okay. So let's just divide all the rows. So 1/7 R1, 1/7 or -1/7 R2, and 1/7 R3. You get 0, 1, 1, 1, 2, 1, 1, 1, 0. Now I've seen students who kind of look at it and say, oh, there are no free variables, so no eigenvector. This is not an REF yet. Okay. So please take a couple of minutes, make sure that it is an REF, and then decide your eigenvectors and so on. So let's kind of swap some rows here, maybe R2 and R1. 1, 2, 1, 0, 1, 1, 1, 1, 0. And you can do R1, R3 minus R1. That's going to be 0, -1, -1. Smiley face is evolving slowly. Look at those two. R3 plus R2. And I'm happy. If you don't get that, please check your work, okay? It's not because there was something wrong with the matrix. Maybe you missed a sign somewhere. Maybe your eigenvalue is wrong. It's very difficult to kind of backtrack, but you have to make sure that you fix it. Okay? All right, so this is a leading one. That's a leading one. X3 is free. You know the process now. So the second row gives you x2 plus u equal to 0. That's x2 equal to -u. And the first row gives you x1 plus 2x2, which is 2 times -u, plus x3 equal to 0. So x1 is u. So if you write a general eigenvector, it's going to look like this: x1, x2, x3. That's equal to u times 1, -1, 1. And for your choice of u, I could pick one eigenvector as v1 equal to 1, -1, 1. And if you are getting bored with u equal to 1, you could put equal to 2. I don't care. That's what it means by saying an eigenvector for each eigenvalue. So of course, in this case, there is no surprise. Mg is 1. Mg is not infinity. Don't look at u being infinite number of cases. So, okay, the geometric, no, this is just one eigenvector. Okay. Now the second one, this is where the interesting things lies. Okay. So lambda 2 and lambda 3, which are both equal to 1. So a minus 1i, which is a minus I, that is 877, -7, -6, -7, 7, 7, 8. Minus the 3 by 3 identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. You get a beautiful looking matrix if you do this. What are the elements of this matrix? It's all sevens. Okay? 7, 7, 7, -7, -7, -7, 7, 7, 7. You already know you're on the right track because you're going to get some zeros there, okay? Which row reduces to, not going to tell a story about how that becomes this 1, 1, 1, 0, 0, 0, 0, 0, 0. That part to this part is left as an exercise for you. Do it at your own convenience. Big question now. How many free variables do we have? 2. Okay. There was no way to predict this before we started doing the problem. We did a 3 by 3 on Thursday where we only had one free variable with a repeated eigenvalue. Okay. Now you have two free variables here. X2 is free, X3 is free. X2 equal to U, X3 equal to V. Please give two different letters for these. Okay, don't give both equal to U. Okay. Which means that you're expecting two vectors out of this. So the geometric multiplicity is 2 in this case. Okay, so it's a number of free variables that you get out of the a minus lambda I, lambda in this case is 1. Okay. And for this is with MA equal to 2. And for this particular example, MG became equal to 2. Okay. It's not always going to be the case. Well, there's only one active row there, the first one. Okay, there's nothing much you could do. So everything has to lie on that plane x plus y plus z equal to 0, right? So row 1 gives you, now do this carefully, okay, because sometimes students, they do crazy things with this. The first row gives you x1 plus u plus v equal to 0. So x1 equal to negative u minus v. So your basis for eigenspace or the null space of that matrix or the eigenvector is x1, x2, x3. And that's equal to negative u minus v, u, v. Now comes the part where you have been doing this for the last 2 or 3 weeks. You need to kind of separate it out into two separate vectors. This is u times negative 1, 1, 0. And v times negative 1, 0, 1. These are two linearly independent vectors. No multiple of this will give you this. No multiple of that will give you this one. Okay. You worked hard for this. You need to keep both vectors when you write the answer. So since you have a geometric multiplicity of 2, you expect two vectors. So v2 equal to, so for lambda 2 equal to lambda 3 equal to 1, v2 equal to 1, negative 1, 1, 0, or any multiple of this is okay. And v3 equal to negative 1, 0, 1, or any multiple of it. Okay. Please don't combine these two things because those are totally different vectors lying in totally different directions. Okay, so you cannot just combine these two and say only got one eigenvector. These are completely different eigenvectors lying in two different planes. Okay, so they have to be linearly independent, and this also confirms that you have the geometric multiplicity is two eigenvectors. So there are places in your problem where you just have to stop before you make more mistakes. This is one such place. Okay, please do not add these two things. Yeah, that's when you have a nice thing going on and you suddenly just spoil it, because then you're back to one vector, the geometric multiplicity changes. Okay. So these are completely different directions, so you have to keep it as such, because you cannot get 0 from 1 or 1 from 0 by multiplying it to the scalar. Okay. Those are linearly independent vectors. Okay, any questions about that? So the only thing you have to keep in mind is this particular part here. Okay. If you get two free variables, keep it as two vectors. Any questions? If you don't have any questions, here is one more bad one for you to do. Because you might be wondering, have you covered all the possible cases in 3 by 3? No. When I'm doing slightly difficult examples, the ones in your homework I think are easier. Okay. Got lots of zeros in them, so it's easy to manipulate those. So do the same thing for the following 3 by 3. -3, -7, -5, 2, 4, 3, 1, 2, 2. All right, so go ahead and try. Sure that the numbers are correct. Okay, so again, expanding along the first row. Okay, just remember that's a -7 here, but when you do the cofactor for this, it's a +7. Okay. Would be 8 minus 6 lambda plus lambda square minus 6. Okay. It's a 4 minus 3 is 1 minus 2 lambda. If I make any mistakes, okay, because I'm kind of copying it from there to here. Everything okay so far? Feel free to unmute and tell me if something is wrong, okay, before I go too far. Lambda square minus 6 lambda plus 2. Right? Don't like the number 19. That is what I'm getting. That's what it is. Now you have to expand it out. Okay, there is no shortcut to doing this. And I know it's not the most appealing thing to do, but let's just do it. It's -3 lambda square plus 18 lambda minus 6 minus lambda to 3 plus 6 lambda square minus 2 lambda plus 7 minus 19 lambda equal to 0. I'm hoping that the silence so far means everything is okay. All right, let's see what we can clean up here. We have a -3 lambda square, +6 lambda square. That's a 3 lambda square. Then you have a plus 18 minus 19. And then you have a -2 here. Okay, that's a -3 lambda. The ones with the single lines under it. The constant terms are -6 and +7, that's +1. And then you have a minus lambda to the power of 3 equal to 0. Okay. So right now the terms are all kind of jumbled up. Let me just organize it and write it in a decreasing order of terms or decreasing degree of terms. That's going to be negative lambda to the 3 plus 3 lambda square minus 3 lambda plus 1 equal to 0. In general, I wouldn't ask you to solve a third degree polynomial because it's a pretty unsavory thing to do. Okay. This one actually has a pretty nice way of factoring itself. Can you tell me what this is? The coefficients are 1, 3, 3, and 1. There is a negative sign that is alternating, but I don't know if you have seen the Pascal's triangle. What are these coefficients representing here? 1, 3, 3, 1. Can somebody tell me what this polynomial would sort of collapse into? I don't know if somebody is saying something or maybe it's another rule. These are the coefficients for, so this is a plus b. This is a plus b whole square, a square plus 2ab plus b square. These are the coefficients for a plus b to the power of 3. Okay. This is what I call the Pascal's triangle. So you can just keep on adding these numbers. 1 plus 2 is 3, 2 plus 1 is 3. So the coefficients here, the 1, 3, 3, 1, are the coefficients of these terms here, the 1, 3, 3, 1 with a negative sign. Okay. So this indeed is the expansion for negative lambda plus 1 to the power of 3 equal to 0. So if you take negative lambda plus 1 or 1 minus lambda, multiply it 3 times, we'll get that. So what are the eigenvalues here? Now can you tell me what the eigenvalues are?
1,
1, 1 3 times. Okay. There's 1, 1, 1. So lambda 1 is 1, lambda 2 is 1, lambda 3 is 1. I don't care which one you call that one. So lambda 1 is 1, lambda 2 is 1. What is the algebraic multiplicity of this? 3. Because it's repeated 3 times. That's the extreme case for a 3 by 3 matrix. Maybe all 3 of the eigenvalues are different, 2 of them are the same, or all 3 are the same. Good thing is you only have to do one eigenvector because no matter which one you take, okay, that one will represent that one. So go ahead and pick your favorite one. I'm going to pick this one. You can pick this one or that one. Okay. So a minus I is, it's going to be a little bit involved because the numbers are all kind of not equal to 1. So negative 3, negative 7, negative 5, 2, 4, 3, 1, 2, 2, minus the 3 by 3 identity matrix. And right now I have no idea how many free variables I'll get. It's a matter of chance now. So it's negative 4, negative 7, negative 5, 2, 3, 3, and 1, 2, 1. That's not at all an REF. We have to do some work. Okay. So that's what we have. All right. Now let's focus on REFing that thing. So let's swap row 1 and row 3. 1, 2, 1. Oh, by the way, you could have checked your trace and all that stuff. Okay, so the sum of the eigenvalues is 3, and if you take the sum of the numbers in the main diagonal, it's 6 minus 3, 3. So just for peace of mind. All right, so let's do R2 minus 2R1 and R3 plus 4R1. Okay, so at last there is hope. Okay, those two rows look right to create a row full of zeros. So you can do -1 R2, R3, whichever order you do it. 1, 2, 1, 0, 1, -1, 0, 0, 0. So for this particular matrix, you had the eigenvalue with the multiplicity of 3. How many free variables do we have? Only one. Yeah, that's the unpredictable part of these calculations. Two basic variables, x3 is free. So mg is 1. You cannot generalize this into a theorem or anything. You have to just take it the way it comes. All right, now let's finish it off. So x2 equal to x3 and x1 equal to -2 x2 minus x3. So x1, x2, x3 is u times -3, 1, 1. Okay, and that gives you what you need. You can now pick your favorite free variable for u equal to 1. You get an eigenvector. That's all you have. Okay. -3, 1, 1. I've seen students being in some kind of charitable mode and say, oh, only have one eigenvector. Let me create two more. U equal to 2, -6, 2, 2, and u equal to 3, -9, 3, 3. Are these useful? You're just creating a multiple of the same vector. Okay, you can create 100 more. Who cares? So only have one eigenvector for this, and that is what is confirmed by your geometric multiplicity. All right, I think I've done enough examples. That is what you need to do from section or chapter 6 actually. Okay, so this is the end of chapter 6 and end of section 6.1. Tomorrow we'll start solving systems of differential equations. That is why we have done all these things. Okay, so we'll start with systems of differential equations and also see how we could relate it to eigenvalues and eigenvectors. That's a pretty cool thing to do. Okay, whatever you have done so far, it's all crazy calculations, but we need to get some applications going here. So we'll do that tomorrow, and maybe some bits and pieces on Wednesday as well if we need to. Okay. All right, so that's it. So do your homework and get some practice with these things. Yeah. Have a nice day.
Thank you.
Thank you.
Thank you.
Thank you.
Glad that everything worked out today well. So that's
Professor,
sure.
I was